physics time. We're going to use teal today, and we're going to first start out by talking about the equation for universal gravitation. Write it down. We're talking about gravity today. I mean, and we've already talked about gravity, and so this is assuming that you know things like W equals mg and F equals ma, and the effect of gravity, hang time, drop time, distance covered by a falling object, free fall, things like that that we have talked about kind of at the beginning of the year, September and October time. And now we're going to talk about the reason, well, not quite the reason why there is gravity, because no one really knows for sure. But we're going to talk about more in depth into the physics of gravity itself as opposed to the physics of the effects it has on the world. Aye, aye? Yep, aye, aye. Tell me it.
Aye, aye.
No, tell. Thanks, but I mean, tell me the equation for universal gravitation.
I got it.
Let's first describe this conceptual. Why would I talk about universal gravitation? What does this imply? Not even really imply, but what does this explicitly state? The universe, yeah. Everything in the universe attracts everything else. Everything that is with mass attracts every other massive object in the universe. Massive here meaning with mass, not massive as in Ty's massive ego, where massive there means just great big. In the vernacular, we use massive to only mean large or extra large or ginormous, as a freshman would say, as one specific Hunter freshman would say. But when I say massive in the universal gravitation, I mean any object with mass. So universal gravitation means that all massive objects attract all other massive objects equally? No. What does it depend on? Let's talk about it right now. Tell me it.
The formula is F equals
F sub g, which you can also rewrite as, what's F sub g? Force of gravity, which you can also rewrite as, what is that synonymous with? Weight. Yeah, it is weight, but we don't usually express it like that. When we talk about weight, we usually mean the comparison between the gravity of an object exerted by another much, much, much larger object, like your weight on Earth. In fact, when we talk about weight, we almost always mean weight on Earth. But it is the same as the force of gravity. It's just that we usually, when we say weight, we mean the force of gravity pulling you towards specifically planet Earth. You do have a weight in the gravitational field of this marker, or Alexa's spleen, or the Pope. You have a weight in the gravity field of those things, but we normally are talking about weight as it relates to planet Earth. Interestingly, as we'll find from our equation, your weight in the field of planet Earth's gravity is the exact same as planet Earth's gravity, planet Earth's weight in the field of your gravity. Because it's Newton's third law. However attracted to Earth you are, Earth is that attracted to you too. So why do you move when you fall and Earth doesn't? We've been over this before, this is a review. Why do you move when you fall and Earth doesn't rise up to meet you? First of all, if you're being pedantic and technical, it does, but just a very little bit, but why? Why? Because it has much more mass, and so F equals ma, you get the larger acceleration, Earth has a larger mass. F sub g, the force of gravity, equals capital G times the mass of the first object times the mass of the second object divided by the radius of the object or the distance between them squared. Either is fine. I've seen it both ways. This is fine. D probably gets, let's put D because it probably does cut closer to the quick, as it were. So F sub g here is weight or the force of gravity. I'm not going to write it, but this means of M1 compared, or of M1 in the field of M2 or M2 in the field of M1. It's the same. But the force of gravity of those two objects attracting each other. It's mutual. It's an interaction. Capital G is the universal gravitation constant. Each of the four fundamental forces of the universe, of which gravity is one and is the weakest and is the longest acting, has its own constant. The universal gravitational constant for gravity, the universal constant for gravity, the universal gravitation constant, happens to be, and I do literally mean that, we can't think of any reason why a universe couldn't work with not just a different gravitational constant, but a vastly different one. There's no, as far as we know, this number is absolutely arbitrary and random. It just happens to be this way in our universe. And we can easily imagine another universe with functional physics having a different universal gravitational constant. But in our universe, it is everywhere 6.67. When I say everywhere, I mean I'm going to change this to approximately equal to, because we're not going to measure it out to 100 decimal places. 6.67 is all that you need, times 10 to the negative 11th, newtons squared, meters squared per kilogram squared. Crazy unit. Why this crazy unit? What's the function of this unit?
To just get it.
Yeah, to just get rid of these to make newtons the answer.
What does the book say? Not Newton squared.
Because newtons squared is wrong. Just newtons.
Okay.
Thanks, Lily, because I'm wrong.
I didn't think
Thanks for humbling me. Things were getting too egocentrical in here. You're right. Newton meter squared per kilogram squared. Thank you. So for this one, you need to know not just what it is or its units. By the way, what's the unit for this one then? Newtons. But you need to know its value. You have to have this value memorized. M1 and M2 are masses measured in kilograms, and d squared is distance. Well, let's just put d is distance measured in meters. Would be the SI base unit in order to make this drop out. Recognize, if you don't change the distance to meters, you have to change the universal gravitational constant. So either convert your distances to meters or change the gravitational constant. If we instead of meters, this were kilometers, would this whole number, would this go up or down? If we were measuring it in Newton kilometers squared per kilogram squared. Yeah, which would it be? You said both. Down. It would go down because we're using a larger unit. And so with this number, these digits, would this go up or down? Up, yeah. This would be a larger negative exponent. It's easier just to convert the distances to meters. To solve these equations, this is not, you'll recognize even a freshman, when I show them this, recognize that this is not complicated math. In your calculator, you type, they might be long numbers, but it's not hard math. You type 2 times 4 divided by 8 times 8, you square it, times, this chunk makes it a little hard to type in, but the math is not hard. It's multiplying exponent. Like this is, when you learn exponents? 7th grade? This is 7th grade math at the best. But what makes it hard is the numbers are large and kind of hard to type in a calculator, and there are quite a few of them, and there is also an order of operations. Do you have questions about this? This is universal gravitation. The book gets into detail quite a lot, and I like it, about the implications of this. Like, there's one really excellent question about if a baby is born, is the doctor's force of gravity on that newborn child greater or less than the force of the planet Mars on it? Which is really, I think that's an exciting, and I like that question. It also goes into deep, it talks about the butter cannon. Do y'all read about the butter cannon? There's a butter cannon in here for you to read about. But other than that, do you have questions about the math of this? This is the main thing to do. No. Okay, let's now move on then to talk about some interesting conceptual questions. This marker's not showing up super hot on the camera, but you have this already? Okay. Let's talk now about gravitational interactions. We're going to talk about falling through a planet, which is impossible, but it's an interesting thought experiment. We're going to talk about tides. We're going to talk a little bit about black holes, and I think that will do it. I think there might be a section here about artificial gravity. So we're going to call this part gravitational interactions. Gravitational interactions. The first is this picture of the gravitational field inside a planet. Listen. The gravitational field of the Earth exists inside the Earth as well as the outside. Remember, it's a convenient physics rule of thumb that we assume an object is concentrated at its, what? An object's mass is all concentrated at its center of mass or center of gravity. We assume it's all its forces, the gravitational forces concentrated at the center of gravity. But that's not really true. We know that's not true, right? Your, as we talked about in rotational dynamics, the configuration of your body does change. When you pull it in, you go spin faster. So obviously it changes things physically. It also changes the way gravity interacts between objects, the configuration of those. So it's convenient for us to think of Earth as that point, and that's where all of its mass is. But that's just not true. What is true is that as we know from the law of universal gravitation, every atom, every massive particle that makes up Earth is attracted to all the other massive particles that make up Earth. And on average, its mass is all concentrated here, but that's just an average. In the same way that the average score on the last test was a 98%, but that doesn't mean both students got a 98%, does it? No, it doesn't mean that. But it does behave that way when we talk about the average. So this says, the gravitational field of the Earth exists inside the Earth, as well as the outside. To investigate the gravitational field beneath the surface, imagine a hole drilled completely through the Earth. So we're done imagining that, and now we're imagining that. This is a big hole, and it's drilled all the way through the Earth. Forget about the impracticalities, it says, such as lava. You know the impracticalities we often forget. Lava, high temperatures, and consider the kind of motion you would undergo if you fell in such a hole. Okay, so here you are. No, you're more exciting than that. There you are, an eldritch horror that you are, Lilith, betrayer of mankind, and you fall in the hole. What will happen? That's an exciting and interesting answer to the question. I don't know if anyone heard. Lily said go down. What does down mean? That's a really interesting question. Well, how do we define down? I mean, you know down from the time that yesternight, Asher fell and hit his eyebrow on the toilet and it broke open. He had to have stitches. But he knows what down means. That's part of what down means. What else? When do you learn what down is? This pin doesn't know anything, but it knows how to go down. Look at this other identical pin. Now how do we define down instinctually? I don't have enough. Yeah, no, you can't say that. In the direction the gravity is pulling you. That's what down means, right? Things get really good. Things are going from dark to darker here, but one of the reasons why cars crashing into water is such a problem that people can and do drown in very, very little water is that, especially if there's been some jostling about and there was some disorientation, when you are submerged in water, you don't know what way down is. You can't. Your body is set up for existing on land. So I'm sure fish that do exist in water have sensory methods that they can tell which way's up and which way's down, but human beings do not. And so, especially if it's dark, the best you can do if you've been in a car crash and you're in the water is pray that the direction you're going is up, because it feels the exact same as swimming down until you get to the point where your ears start popping, and guess what? You just got in a car crash, so you're freaked out anyway. So if you remove the things that we're normally set up for to determine which way is down, the question of what is down really becomes problematic, or at least interesting. So what is down? We often define it as just the direction of gravity. So as you're falling, you fall down. You fall towards, again, pretending Earth's center of mass is here. You fall towards that. How much do you fall towards that? We already know from chapter 2. In this first second, you fall a little bit, and a little bit more, and a little bit more. What do we call that kind of motion? What do we call that kind of motion? Where it's going faster and faster and faster. It's acceleration. It's one kind of acceleration. It's one kind of acceleration. It's getting faster as it goes towards the center. Is that still true? Are you going to go faster and faster and faster forever until you break free of this and you're going the speed of light? No. And fate's going to tell you can build a railgun like this? No? No. The answer is obviously no. I phrased that in such a way that you know the answer is no. What's going to happen? And once you're here, no, we're ignoring the impracticalities of lava and heat and death.
Oh, we're ignoring death.
Yeah. So now that you're here, what? Which way are you moving? You just float. Is that the answer? No. You're still moving, but why? Yeah, you're in a state of like nasty undeath. You're incapable of death, and so you just sit. It's suspended in motion for eternity, and that is a special kind of hell. No, it's not just purgatory. It's hell. No. Why? Now you're still moving because you have inertia. But now you are still moving, but you're going to be moving slower and slower. And by the time you get to here, guess what? You're moving the exact speed you were when you started at the other end. Yeah, assuming it's perfectly circular. If you started at the North Pole end, you'd fall and gain speed all the way down to the center, then overshoot and lose speed all the way to the South Pole. You'd gain speed moving toward the center and lose speed moving away. Without air, another nice thing to forget about. Also, you can't die. So you're asphyxiating, you're roasting, but you cannot die. The trip would take nearly 45 minutes. Isn't that interesting?
Wow.
If you failed to grab the edge, you'd fall back toward the center, overshoot, and return to the North Pole with the exact same amount of time. Yeah, like Portal.
You are.
Suppose, it says, you had some way to measure your acceleration during this trip. At the beginning of the fall, the gravitational field strength of your acceleration would be g. Are you accelerating at g the entire time you're going down here? You would be if this were this situation. You were on a tower, and you were falling. Remember, down is just towards the center. You would be accelerating at g the entire time. Why are you not accelerating at g as you fall towards the center? Why does it work here, but not here? What's the convenient thing that we ignore in physics? What's a convenient? It works everywhere up here. It always works up here, but once we go into the Earth, it doesn't work. No.
Well, air is not even Air is not here. Center of gravity.
Yeah, because out here, it's a safe assumption that all the mass is concentrated at the center. But once you start falling down, like if you're here, there's some mass. This amount of mass is now pulling you up. So not only are you accelerating, but your acceleration is decreasing. So it starts out as g here. So your motion changes, but your acceleration changes. Here it's g, here it's 0. So your acceleration decreases too. You have like a meta-acceleration, a change in acceleration that's called, I think, jerk. I think jerk is the change in acceleration. So where displacement is no differentiation. Which kind of calculus is where you're dealing with the going up of exponents? Is it differential or integral?
Going up of x.
Yeah, is that differentiating?
Integral.
I don't know.
Yes,
Anyway, where the first integration is displacement, the next is velocity. So displacement divided by time is velocity. And then that divided by time is acceleration. And then that divided by time is jerk. There are more exponents of these, but I think it's jerk. You might have to look it up. But your acceleration, not only is your motion changing, obviously your displacement is changing, you're moving. Obviously your velocity is changing. That happens every time you fall. But also your acceleration is changing because there's less and less matter below you and more matter above you. What is weightlessness? Word changing. What is weightlessness? What is weightlessness?
Non-gravity.
Can that ever happen? According to what we just said, no. So there's no such thing as true weightlessness. When might you feel weightless? When might you experience the feeling of weightlessness? When you are falling. When you are falling. Here's one you feel. This is your mom's car. This is you. I guess your mom's probably in it too. She's over here somewhere. It doesn't really matter. But you're on West Ash. And you driving. She's driving fast because she doesn't value her or your life, and she has to get where she's going. So you go over this hill, and And you feel in your tummy, you ever feel the tummy thing on West Ash? Do you specifically feel it on West Ash when you're driving with a reckless driver like your mom?
Yeah.
What? Yeah, me. Have you done it? Yeah, it was you. You weren't there, but you were. Yeah. You probably felt it in your tummy when I was driving you on West Ash. The reason you feel that is because you're in free fall. What? I mean, you see in the movies that the car is all the way off the ground. Probably that's not wholly, I would hope it's not that bad. But that feeling is because of weightlessness. Not because gravity has ceased existing, but because you're falling. That's what weightlessness is. And the reason I say this is that the other example your book gives is, this is supposed to be an elevator. The elevator is not, forget about this old drawing. The elevator is on a pulley, right? And if the elevator cords snap, now the whole thing is falling. But since you're in an elevator, a non-glass elevator, you don't see motion. You just feel weightless. And it might be blissful, right? Like if you were a child or a moron who didn't understand that things can be scary because of this, you're just like floating. And that's great. And that's just like this next thing, which is Space. Yeah, thanks, Ty. This is Spaceman. This is Spaceman.
This Buzz Lightyear.
Yeah, this is Spaceman. Because this is stupid. You know this. Like, obviously, I just said, if you're a child or a moron, you might think this is fun, but this is scary. You know you're falling. This, even a child or a moron would know they are falling because they can see outside. But both of these feel like weightlessness. Now, take both of those to this. It's very possible for a not moron, because they don't think about it. Well, they still are a different kind of moron, but people who don't think very hard about things, to just think that the spaceman is weightless because he's escaped Earth's gravity. People say that, in fact. They say that they're outside of Earth's gravity, and so there's no gravity there. But you know that that's not true. What is true of him, just like is true of the elevator, and just like is true of your mom's car? He's falling. Because if you look at, let's go back to the drawing of Earth. If you look at where spaceman orbits, even like the ISS, I'm going to try to draw a roughly scale diagram. We're going to have to remove all this non-scale stuff here. But here's Earth. No, it's on the other side. It doesn't matter. Here's Earth. I'm going to try to draw roughly the scale. I think the ISS orbits about like here. Like that's not the International Space Station. It's not a long ways away. It's not a long ways away. In fact, it experiences about 99% of the gravity that Earth does. Why is it weightless then? And how can it do that for so long without crashing? It's not because it's spinning. It's because it's not spinning. It's orbiting. It's orbiting. And orbiting is falling but missing. Falling but missing. How do you miss? How, though? How do you do that? Because you're going... No. Yeah, because your tangential speed, what according to Earth would be horizontal speed, is great enough that Earth, since it's curved, falls away. Like you're falling, but your Earth's curving away at the same rate that you're falling. So this doesn't work. Here's Cape Canaveral where rockets are launched from. This doesn't work. Just get it as far away as you can, because everything, just like, I'm running out of things to throw, just like this is not different in kind. Pretend I caught it. That motion, Mr. Keim throwing a pin, is not different in kind from a rocket launch. It's just different in magnitude. I'm not throwing it 10,000 miles an hour, but I am throwing it, and when it comes down, it comes down. If a rocket launched at 10,000 miles an hour, it would go a long ways, a lot longer than a pin, but it would just come right back down. Because what is down? The direction of Earth's gravity. So how do you get in orbit? This doesn't work. You can't get far enough away from Earth to not be in gravity anymore. That does not exist. You can't do it. So how does orbit work? You have to be going faster in the other direction. You have to be going faster horizontally. So what they do is you launch from here. I'm going to draw the right way in a different color because you'll need this for Kerbal Space Program. Launch enough out that you're no longer interacting with the atmosphere. The atmosphere is bad. There's going to be friction, a fire. Don't do with that. Go up far enough away that you're not in the atmosphere, and then turn. And now all of your motion should be horizontal, and you start going in a circle instead. You're going fast enough, not up, but fast enough that way that you miss the earth when you will go to fall, and that's weightlessness. Tides and black holes you can read about on your own. I will give you some very basic information about tides, which is another misconception. So this was probably misconception number one that should have been cleared up when you were a freshman, is that everything exerts gravity. It's not just big boys like Earth and the sun. Everything exerts gravity. Misconception number two is that he's just falling. Weightlessness is just falling. There's no such thing as zero gravity. When people say zero G, it's falling. That's how when they do astronaut training, the way they can experience what's called zero G, or sometimes called microgravity, or more correctly called weightlessness, is just an airplane, a normal airplane that goes like this. And this is the airplane, and it flies just like that. And on the way up, the speed of the airplane, the acceleration of the airplane is added to the acceleration of gravity, so you experience 2G here. You're squooshed into your seat because you're experiencing 2G. And on the way down, you experience 0G. Not zero gravity, 0G, meaning free fall, weightlessness. Yeah? That's misconception number two. And the misconception number three is getting into space is not, let's get far enough away from Earth that we're not being dealt with by Earth anymore. It is, let's go fast enough around Earth that it falls away as we move along. And that's called orbit. Now, misconception number four is the tides go in, tides come out. You can't explain that. The tides, why are they caused more by the moon here? This is not to scale anymore, but BT dub. Than by the sun. The sun is a bigger boy. The sun has more gravity. Why is the tide caused more by the moon than the sun? Because it's closer. Because tides are about difference in gravity. Tides are about difference. I'm just going to write it over top of all this other stuff. Tides are about difference in gravity. In fact, we call that the tidal force, F sub T, tidal force. It's about the difference in gravity. Does the sun exert any tides on Earth? Sure. But if we were to try to draw a scale drawing and it was like this, God bless you, there's a sun slightly larger, there's the moon itty bitty bitty tiny, and we draw like a number line of the sun's gravity, one solar gravity is there, and then what are we at the other side of Earth? Like 0.999999999, lots of nines, solar gravity. Whereas for the moon, here we're at 1 lunar gravity, and here on the other side of Earth we're at like 5/6. I mean, it's a much larger, or a much smaller fraction. There's a much bigger difference in gravity, and that's what the tidal force is difference in gravity. Does that make sense? No? What? Say it.
No.
It's about...
I have nothing to say.
Say it, then.
Oh, okay.
Does that make sense?
No.
Okay, why?
I'll have to figure it out later. Continue
What
on.
is the difference? I mean, no, this is the last thing. So, I mean, you're going to read about black holes on your own.
Uh-huh.
It's because it's different. Size.
Got it.
It's because of difference in gravity.
Yep. That's clear. I got it.
No, you doesn't.
How do you know?
I don't know. I'm trying to think of how I can use this to... So this, we can pretend this is the whole distance from the Earth to the sun. It's about fractions. You know about fractions? Let's pretend this is the whole distance from the Earth to the sun, okay? And let's say the width of the Earth, this is not to scale, but let's say the width of the Earth is this much. That is 2 millimeters.
Okay.
So from one side of the Earth to the other is 2 millimeters. This side of the Earth
Yes.
is experiencing the sun's gravity 1,000 millimeters.
Yes.
1,000 out of 1,000. This side of the Earth, the other side, is experiencing 998 out of 1,000
Okay.
gravities.
Yes.
So the ratio there, this side compared to the other side, is 998 thousandths,
Yes.
which is almost the same. Like it's almost 1. You know about math. But if this is where the moon is, we'll say that's about to scale. That's 10 millimeters. So now even though the gravity is less, this side of the Earth is experiencing 10 moon gravities. The other side of the Earth is experiencing 8 moon gravities. So there's a bigger difference, you see?
Yeah.
And that causes a tidal force. That difference is the tidal force. So what that means is that get out of here, 8/10. The moon pulls more on this side than the other side. And so there's a bulge in not just the water, but the land, and that's called a tide. And then the other side gets a bulge too because Earth's spinning. You know about, oh, where'd my thing go? Hold on. This thing. Oops, broken. Hold on, let me fix this thing. This is a cool thing that the 8th graders made for me because they were required to. When things spin, pizza dough is out, right? Like when you spin pizza dough. And so as the moon pulls this side more, because it's spinning, it also pulls the other side out more. It's even doing a pretty good job in my little model here. If I pull more on this side than the other side, the sides that are closer to the center are now the sides perpendicular to where I'm pulling. The side across from it gets a little bit pulled. The sides perpendicular don't. So that's the tides. That's the tides. That's the tides. That's the tidal force.